Great. Well, thank you, Andy. It's such a fascinating topic. I learned several things on that talk, actually, so thank you very much. And I've been at it for a while. Yeah, so got a session now from me on some of the different sources of PNT beyond space. I'll cover that, and then there are a couple of case studies from Guy and I, just very light touch case studies, one in aviation and one in the mobile phone. Maybe I'll run on from my talk and do that, and then hand over to Guy, and then we can open up to a Q&A with some flexibility. So yeah, what about sources of PNT beyond space? Well, here are some examples. Maybe I would suggest some of the key examples, and none of them are a substitute for GPS or GNSS. And I thought Andy mentioned that very clearly indeed. I think his words were, we'll never be not using GPS, GNSS, at least not in the foreseeable future. And absolutely, it's so wonderful, so accurate, globally available for free. Why wouldn't you use it? So these are very much augmentations. Some of them are independent positioning, but none of them are the perfect answer. So you often end up using them in combination by going through some of the approaches we've talked about today, with looking at your requirements and your risks, and then choosing what you want to put in your cocktail blend, if you like. So I'll just, next few charts, I'm just going to go around this hexagon, is it? 2, 4, 6, yeah, hexagon. I'm just going to go around this hexagon and just highlight a few of the key technologies that are being used and that are becoming available, all with the aim of generically resilient positioning. So this has come up a few times already, dead reckoning. And what do we mean by that? Well, classically, we mean a combination of gyroscopes and accelerometers. And these come in a variety of form factors, from the very inaccurate and very cheap, right up to the extremely accurate and not only very expensive, but also not available to non-civilian user categories. So right up to so-called ITAR controlled systems that would cost several tens of thousands of pounds to procure, high-grade inertial sensors, all the way down to the sort of sensors you get in your mobile phone. So the way that they work is you combine the gyroscopes and the accelerometers into an inertial measurement unit to give you a delta position from an initial reference. So that's why it's dead reckoning. It doesn't give you absolute position. You need to have the system initialized or initiated with a position. And then these systems will give you delta position and delta orientation from that initial position. How do you get the initial position? Well, the most common answer to that is to use GPS, which obviously has its pros and cons, as we've just been talking about. And you can see in the bottom right a diagram which shows really the range of variability in how quickly high-grade inertial sensors drift versus low-grade inertial sensors. So the blue line is a low-grade sensor, and in this example, in about a minute, it's 100 meters of error. So kind of unusable for navigation. In fact, it becomes unusable for navigation in a fraction of a minute. So these are the types of sensors that you'd see in your mobile phone. And therefore, they have to be recalibrated on a regular basis. You can also see in the red line that for what's generically called an expensive MEMS, so solid state IMU, it's got a couple of minutes and only 10 meters. So that's an order of magnitude different. And there's a grade of inertial measurement unit that's more accurate than that, which would be the military systems. And then the holy grail that's been talked about for a while and is getting closer is to use cold atom quantum sensors, which may be able to give several hours worth, or maybe even more, of navigation level accuracy, so sort of 5 meters or less. So that's a whole key area. And the beautiful thing about these is that they are autonomous, these inertial sensors. So although they have their cumulative inaccuracy, they are autonomous and not really subject, I mean, that's a bit of a sweeping statement, but generally speaking, not really subject to interference, jamming, spoofing, and so on. I mean, there are certain things you can do to upset them, but fundamentally, they are very resilient. So if you combine this with a reinitiation, you've got yourself a resilient navigation system, as long as the reinitialization can be trusted. So there's a key option, very, very commonly used, very, very useful. In fact, some proponents suggest that a decent navigation system should use inertial first, and then just recalibrate using something like GPS. And there's a lot of merit in that argument. And that certainly applies in the case of high-grade military systems, such as missiles and jets. Ah, yes, terrestrial radio. So here's a whole lecture on just 2 charts. So I think you mentioned it earlier. So yeah, I always think about these 3 because they are the most predominant today. So pretty much all mobile devices, smartphones, use these 3 plus GNSS to give you a blended position. Cellular positioning, Wi-Fi positioning, and Bluetooth positioning. At their most basic, they use, actually at their most basic, cellular positioning is just what's called cell ID. So my mobile phone is connected to one or maybe a couple of base stations. So with that knowledge alone, it can figure out that I'm in this part of Cornwall rather than somewhere else in the country. So there's a very coarse positioning from cellular. The next level is to measure the signal strength to those 1 or more nodes. And by the way, this applies across all of these technologies. Cellular, Wi-Fi, and Bluetooth. So you can measure the signal strength, and from that you can get an indication of distance to the transmitter. And if you've got a couple of indications of distance, then you can calculate your position based on that information. The problem is, well, the problems are many actually. Let's say here I've got half a dozen Wi-Fi access points for the sake of argument. Well, they're first of all not all in this room. Some are probably in reception, some are probably upstairs. They probably are geolocated in the databases, and that's often done through crowdsourcing, sometimes through survey. So my phone's measuring the power levels from those different half a dozen, in my example, access points. But it'll be calculating the position based on the assumption that it's like a free space loss between them, and it's probably not. They're probably coming through the ceiling, or maybe they're passing through other obstructions and so on. So it's a flawed method, and therefore only gives of the order of a few tens of meters at best of accuracy. Often it's more like 20, 40, 50, 60 meters, I would say. So kind of handy, but not really the answer if you want to do indoor navigation, where you need to know where you are within a room. You need a few meters or better. So to solve that, there's quite a lot of innovation going on at the moment in measuring the time of flight from the transmitter to the mobile And in that way, you can get a much more accurate idea of the location of the mobile. So that's called RTT, round trip time. So in simple terms, a ping or a pulse would be sent, time stamped, and when it comes back, time measured again, measure the difference, cut it, speed of light. You've got a reasonable measure of distance, and that I have to say is still evolving from my understanding, but should take us to really quite good accuracies, maybe 10 meters or better. And then some of these technologies are quite dense. So, there can be lots of Bluetooth access points in a building, and some situations, Bluetooth access points are kind of being planted, around retail situations, for example, would be the classic example, where, you'd have multiple Bluetooth access points specifically to allow zonal location within the shopping mall or the shop or the building or whatever it is. So these are really quite useful and widely used technologies. And there's an example of how the fingerprinting works. So this mobile device is measuring signal strengths, sending that information to a server where the database resides, and that database then does some fingerprinting and determines the location and sends that back to the device. And sometimes that's done over what's called the control interface, and sometimes it's done over what's called the user interface. So the control interface is the signaling system for the phone, and the user interface would be more like a text message type format. This, by the way, was driven by the need for emergency location. So in America, you may have heard of E911, and in Europe, it's called E112. And there was a requirement put out for a mobile device to be able to determine its location. I think it was to 100 meters within 95% accuracy. And to cut a long story short, you can't do that with GPS because it doesn't work indoors generically. So Wi-Fi positioning and cellular positioning were used to meet that regulatory requirement. Other techniques, which I'm going to do quite a light touch on. Yeah, a lot of what we've talked about has been an attempt at absolute positioning. So with the goal being to give you a latitude, longitude, and height. But that's not always particularly helpful. And I alluded to that in my first talk with that example of the map not being consistent with the satellite image of where the road was. In those cases, it's much more useful to have a relative position using sensors. And in some cases, those sensors can actually dynamically generate a representation of the map or the position of the vehicle within an environment. And that is sometimes known as SLAM, simultaneous location and mapping, dynamically creating a scene, as you can see there in the diagram, relative to the vehicle or the mobile. And it's got quite sophisticated. That diagram in the bottom right, you've probably seen that diagram. It's a very, very popular one. Shows the, frankly, quite bewildering array of sensor-based systems on that are potentially available to a modern vehicle. Some are good at short range, some are good at long range, some are good at measuring distance, some are good at creating a scene, and so on and so on. And a lot of processing behind that as well. Very complex. The camera is often the most used sensor on today's prototype sort of autonomous cars. And I think, well, it's certainly my view, and I think it's a growing view, that cameras on mobile devices are underused for positioning. And this is just a small example of that. So this is an experiment that was done, or some research that was done, more accurately, by Nottingham University a few years ago. And it was to try and use the camera on a mobile device to look at somebody walking across grass. And the hypothesis was that grass would be actually really quite difficult because it all looks the same, right? One blade of grass looks a bit like another blade of grass. But even using the sensor in what I believe was a mobile phone, they managed to, this is the blue lines on the right, they managed to have enough resolution with the processing behind it to show relative movement over a fairly difficult, challenging surface like grass. If you then translate that to a much more structured environment, like a room, for example, which is, I'm looking at a room now that's got tables, windows, door frames, patterns on the carpet. If I was to walk through the room with my camera, then vectoring off those quite distinct features of the room is arguably much simpler, a vision-aided inertial navigation type problem than walking over grass. So it's really quite possible. And other sensors in the phone are being used more and more. A recent example where I know there's some research is using the microphone and speaker as a kind of a radar type system in the phone. So send an ultrasonic sound and listen for it coming back. We can't hear it, it's ultrasound, but the phone microphone is good enough to do it. And all of a sudden you can get a image of your environment just by using another sensor that's not currently used for positioning in the phone. And you blend all these together to give you the answer to the question, which is, where am I absolutely, or where am I relative to my environment? I put this on blown up because philosophically it scares me quite a lot. Not from the perspective that I'm going to get mowed down by an autonomous vehicle or that I'm going to die in one, but from a system engineering perspective. I mean, I've sort of lived my professional life developing or specifying and helping develop products and services, and keep it simple has always been a mantra, really. And this is a jolly complex system with so many interactions and inputs, most of which are probably very noisy and or inaccurate and or even possibly misleading, subject to spoofing and interference. It just overwhelms me, and I'm kind of in awe of the work that is happening in a fairly structured way to try and synthesize all of this into a usable, safe system called the autonomous vehicle. It really is quite impressive. But having said that, I can't believe that if I was working on it, I'd ever strive to have something as complex as this. I think it's possibly, there's a whole theory about what form factors devices end up on. And, mobile phones didn't start looking like this. You remember the Blackberries, and then they had little keypads at the bottom, and then there were devices that folded out, and all sorts of different ideas as to what the perfect mobile phone would be like. And it took probably 5 or 10 years to evolve into what we use today. And I suspect the autonomous vehicle will be the same. This is more of a art of the possible view, in my humble opinion. And I think there'll be some winners and losers, and we'll end up possibly with a simpler system with perhaps more back-end processing. But that's just my gut feel. I'm interested, as they say on YouTube videos, in your comments down in the chat. I'm going to do my case study, and then I'll hand over to Guy just for sort of consistency. Flow rather. So here's an experiment you can try at home. And I know I'm a bit sad when it comes to positioning, so I quite like doing this. You might find it completely boring, but here it is. So driverless car is a really challenging thing to achieve, as you can see on the right here. It really needs, going back to the ACAI, excellent performance on all of those areas. Mobile phone, by the way, I've never seen this written down from a phone manufacturer. This is just me interpreting what I've observed to be the case. Isn't actually so worried about accuracy as it is about availability. And they ruthlessly prioritize all these different sensors to make sure that the availability is very, very high. To the earlier question from Simon, I think it was, I've put continuity as not so important, because quite frankly, if your mobile phone stops giving you a position, it's not the end of the world. But in order to get a good experience on most of the apps, you need to have a very high availability. Otherwise, the experience is going to be very poor. You kind of know when your phone has stopped producing any position and the app just stops working. So here's the little experiment, just 3 charts, I think. So there's your blue dot. And already, actually, you can see on the left, there's a tiny light blue circle around the blue dot, which is significant. So most people wouldn't be interested in that, but it is significant. It means you've got a higher accuracy position on the right than on the left. And to achieve those 2 effects, this was my mobile phone about, I don't know, 5 or 10 years ago. That on the right is an open sky position after the positions settle down. So that when you don't have that light blue circle, you probably are at the 2, 3, 4 meter type accuracy level. And here, I think I was in a hotel, if I remember rightly, in Romania. Well worth visit, lovely place, Fusteni. So I was in a balcony in the hotel. I went back on the balcony, and all of a sudden, half the sky was gone. Concrete hotel building, half the sky is gone, and you could already see on the left here, my phone going, oh, hang on a minute, this doesn't feel quite so good, and it just brought that little blue ring a little bit bigger, and that's because the geometry to the GPS satellites was suddenly half as good as it was before. So that was the first indication. I then went right into this hotel, and it was a concrete building with, you know, metal girders, and anyway, long story short, GPS stopped working. It was denied inside the building. And this, you can see on the right here, is Wi-Fi positioning. And I know that the map hasn't got a scale on, but you can see at a glance that it's, you know, of the order of 20, 30 meters, something like that. So that's received signal strength Wi-Fi positioning. And then if you get to that point and you turn your Wi-Fi off, which is what I did next, you can actually see the blue dot. It literally just goes, doesn't have a sound effect, but it does go like that. And that's cell ID or cellular positioning, I don't know which, but you're of the order of several hundred meters of inaccuracy. And I, you know, just have a play around if you want to see how your phone's algorithm works by forcing it into these different states. You could probably replicate that fairly easily.